Thank you, and I would like to thank the organizers for inviting me to present my work here. What I will be discussing today is something that I have been doing with my collaborators at Swansea University. So I will be discussing certain modified cosmological scenarios and how they can leave their imprints on the primordial gravitational wave spectrum. So this is the outline of my talk. After a brief introduction, I will again briefly describe the generation of primordial gravitational wave spectrum in standard cosmology. Then I will discuss the modified scenarios of my interest, and I will specifically focus on two types of such scenarios. Some are phenomenological cases and others are motivated by deep brain cases. And then I will finish with a summary of my talk. So this is an illustration of the expansion history of the universe. As we know, the lambda CDM model together with inflation can account for most of the cosmological observations that we have today. Specifically, the predictions of Big Bang nucleosynthesis, BBN, which happens around this time here, those are compatible with observations. And what this shows is that our current concept about the evolution of the universe after BBN are backed by observations. However, this leaves a window of time from the end of inflation to BBN, which is not so well constrained. And so if there were certain non-trivial dynamics happening during that period of time, it would not interfere with BBN and hence would still agree with the observations. So this is the domain of my interest that I will discuss here. So this is a brief description of the generation of primordial gravitational wave spectrum in standard cosmology. I will not discuss this in detail because Tanmoy has already discussed this very nicely in his talk. I will just say that the main quantity of interest is the relic density of the PGWs, the primordial gravitational waves, which is given by this expression here. And rho c is the critical density of the critical energy density of the universe. So here I will just present the two equations which are very important for my subsequent discussion. The first is this fractional energy density in PGW. This is the quantity of interest. This is the observable that I will be focusing on. And as you can see from this equation, this quantity is directly proportional to h, and the subscript hc here refers to horizon crossing. So this means that the quantity omega GW k h square, it is directly proportional to the Hubble parameter when the mode k crosses the horizon. So as we can see from this equation, if we have an amplification in h, that will lead to an amplification in the PGW spectrum. The other thing is the PT that is here, that is the amplitude of the tensor, the primordial tensor power spectrum. And in this work, I will consider that this spectrum is scale invariant. So it will only depend on R, which is the scalar to tensor ratio, and the AS, which is the amplitude of the primordial scalar power spectrum. The other important quantity is the frequency of gravitational waves that are observed today. And that is F0. And as you can see from this equation, it is directly proportional to the temperature. So the events happening at higher temperatures, which is what is of our interest here, those will leave their imprints at correspondingly high frequencies. And that is again what we will see in the subsequent discussion. So this is the generalized scalar tensor setup that I'm interested in. This is the total action. And if you look at S phi, it has these two factors, C of phi and D of phi. These are the conformal and disformal factors respectively. And they together lead to the disformally coupled metric, which is given in the last line here. And in this work, we will consider different combinations of the conformal and disformal factors and check their imprints on the gravitational wave spectrum. The two types of mainly cases that I will consider, one is the phenomenological case, where we consider the m to be 0 and b, the small b here, is 1. So if m is put to 0, that considerably simplifies our action. The second part that I will consider is the deep brain motivated scenario, where m will be not equal to 0 and b will be put to 0. And that will again lead to different kinds of imprints. So what from this action, what we can do is we can obtain the equations of motion that governs the evolution of phi, as well as that will govern the evolution of the expansion rate, that is the Hubble parameter. In the general case, these equations are actually coupled, and they are complicated. They cannot be solved analytically, so we will resort to solving them numerically. So first, the case I will consider is the phenomenological case. And here there is a causality constraint which will relate C and D, the conformal and disformal factors. And they will be related through this first equation that I have put here. So at first I will consider a simple case, which is a purely conformal case where D is equal to 0. And in this case, as we can see, the causality constraint is automatically satisfied. And the other advantage of this case is that the equations of motion can be decoupled and they are rather simple. So I have put here the equation governing the evolution of the field phi. There are three terms in this equation. The third term, which you can see on the second line, that term acts like an effective potential, and it is governed mainly by the evolution of the behavior of alpha, which is the derivative of the logarithm of the conformal factor. The other thing that you can notice here is that it has this quantity 1 minus 3 W tilde. Now, W tilde is the equation of state parameter. In the very early radiation dominated era, this W tilde is 1/3. So this quantity is actually 0. So in the very early stages, this term will not contribute to the evolution of phi. In that scenario, we can easily obtain an analytical approximation for how phi evolves. And we will see that phi n, that is the velocity of the field velocity, that drops exponentially. And that subsequently leads to the value of phi itself dropping, and then it goes to a constant. However, there is a non-trivial effect here. When the temperature of the universe decreases, the particles that were in thermal equilibrium, they start becoming non-relativistic one by one. And that leads to non-trivial contributions to this equation of state parameter. So on the right-hand side, I have plotted the behavior of the kick function. The kick function is this function 1 minus 3W. In the very early radiation dominated era, this is 0. But when these particles start becoming non-relativistic one by one, this has this kind of non-trivial behavior that you can see in the inset here. So at this particular points of time, there will be non-trivial contributions to the evolution of phi, as you can see from this equation. So here I have considered a specific type of conformal factor, which is given here, and I have chosen the parameters B and beta such that it is compatible with observations. And on the left-hand side, I have plotted the numerically obtained evolution of phi, and on the right, I have plotted the conformal factor itself. I have plotted it for three types of conformal factors. The solid line corresponds to this C phi, the dashed line corresponds to C phi square, and the dotted lines correspond to C phi power 4. So as expected, the value of phi falls, then goes to a constant. And then when this kick function starts working in the equation of motion, the value of phi starts changing, and then it evolves as the equation of state parameter changes. Also, as expected, when we take higher and higher powers of the conformal factor, it gets amplified more and more, as you can see here. So the Hubble parameter is directly proportional to this quantity. So we can expect that the Hubble parameter will also get amplified. So that is what we see here, that the expansion rate, which I have plotted on the left, that is amplified the most in this dotted case, which corresponds to C phi to the power 4. And this is even more prominent when we look at the primordial gravitational wave spectrum itself. As you can see here, for the dotted case, which is C phi power 4, it has the maximum amplitude, and it should be detected by the future GW experiments. Also, the other thing to see is that the overall behavior of the primordial gravitational wave spectrum mimics the behavior of the conformal factor itself. That is, it has a plateau. Now I will consider, on the other hand, a purely disformal case, where I will put C to 1 and D is not equal to 0. In fact, so in this case, the causality condition that we had seen before, that is modified to this form. And I will consider two different types of disformal factors. One is a constant, the other is field dependent, where D is proportional to phi square. So I have plotted both of them here. I haven't written the equation because the equations are coupled and they're more complicated. But I've plotted them here. The solid line is the constant disformal factor, and the dotted line is for D proportional to phi square. Their evolution is overall has the same shape, but the amplitude changes. And on the right-hand side, I have just shown that the causality condition is, we have chosen the parameters such that the causality condition is always satisfied throughout the evolution. And now we calculate the expansion rate H, and you see that corresponding to the blue line, which is the GR expansion rate, there is a substantial amplification for both the cases, for both choices of disformal factors. And again, this can be seen in the PGW spectrum on the right, where you can see that both the solid line and the dotted line show amplification. The gray plots that you see here, that is actually for a different choice of initial condition. So what it shows here, that if we choose our initial condition at a lower temperature, then this peak, the shape of the spectrum, that is shifted accordingly. It is shifted to a lower value of the frequency. So in this way, we can shift the peak of our spectrum, and they can again be detected by future experiments. The next one is the D-brane scenario, which in contrast to the phenomenological scenario, has this sort of a normalization condition instead. And first we will consider a purely disformal case where C is 1. So D is actually 1 by m power 4, which means that D is actually a constant. Oh, m here can be related to the tension of the D-brane, but it is a constant. I haven't plotted the evolution of phi here because it is very similar to what we saw just in the previous case. And I have plotted the evolution of the expansion parameter H, and you can see that it shows a peak with respect to the GR value. And if you look at the PGW spectrum, you can see that there is again a peak, and this peak is actually amplified a lot more with respect to what we had seen in the phenomenological scenario. But again, if we choose the initial condition suitably, this peak can be shifted. And of course, they should be seen by the future GW experiments. The last case that I will consider is the field evolution for conformal plus disformal case. This is the case where this is again a D-brane scenario, but instead of putting the conformal factor to 1, which we had done in the previous case, here we choose the same conformal factor that we had chosen for the first case. So that conformal factor is dependent on phi. So since the conformal factor is dependent on phi, due to the normalization condition, the disformal factor will also be dependent on phi, but they will always be related by the normalization. So in this case, again, we have to solve the complicated coupled set of equations, and we find this that the evolution of phi looks like this. This is very similar. If you remember, this is very similar to what we had seen for the purely conformal case. So this shows that the evolution of phi overall is mainly governed by the conformal factor. Because in spite of the presence of a disformal factor, it looks very similar to the purely conformal case. Again, I have plotted for the choice of C phi, which is the solid line, and C phi square for the dashed line, and C phi power 4 for the dotted line. As expected,
Debika,
yes.
Please wind up. Yeah, you can wind up.
Yeah. So as expected for C phi power 4, the amplification is maximum. And this can also be seen in the behavior of the PGW spectrum as well as the expansion parameter. It is maximum. It is lesser than what we saw in the purely conformal case, but it should be detected by some of the future experiments. So to sum up, there can be modifications to the expansion rate of the universe, which can leave imprints on the PGW spectrum. And we have studied the effects of such modifications in the presence of conformal and disformal couplings. And we have shown that they can lead to amplification of the PGW spectrum, which should be detected by the future gravitational wave experiments. Thank you.